Question 1, the structure formula of iodine is represented below. The question was, what's the chemical formula of iodine? So first, to determine the chemical formula, I have to count the number of carbons that I have. So first I have over here 1 carbon, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 carbons. So we have 15 carbons. Now let's count the number of hydrogen that we have. First, I'm going to add the hydrogen. So here we're going to have 2 hydrogens. Here we're going to have 3 hydrogens. Here we're not going to have any hydrogen as the carbon is already attached to 4 different groups. Here we're going to have an extra hydrogen. Here we're going to have also an extra hydrogen. Now for this one, we are not going to have any hydrogens. And for this one, we're not going to have any hydrogen. Same for this one. Now here we're going to have 3. And here we're not going to have any hydrogens. Here, 1, 2, 3, and 4. We're not going to have any hydrogen. Here it's going to be 2. Here it's going to be 2 hydrogens. And then this one is going to have 3 hydrogens. So I think it's better to draw it again and then determine the number of hydrogen atoms that you have in this drawing. And of course, we shouldn't forget the hydrogens with the hydroxyl group. And now we can count the hydrogens. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So we're going to have 20 hydrogens. So it's going to be 20. And we have 4 oxygens, so it is O4. Now this is going to be the chemical formula of iodine. Now in the next question, they said, how many chiral center does this compound have? And a chiral center is a carbon atom that is attached to 4 different groups. So let's find out how many chiral centers do we have in this drawing. So first, I'm going to start over here. Now this carbon is attached to 2 hydrogens, so we have similar atoms, so it's not a chiral center. Now this one over here is a chiral center as it's attached to this group, to this one, and this one, and they are all different. So I'm going to put this as a chiral center. Now remember that any carbon group that is attached or that has a double bond is not actually a chiral center. So this one over here is also a chiral center as it's attached to the OH, to the hydrogen, to this group, and to this group. So it's attached to 4 different groups, we can say over here. So now we have 2 chiral center. Now this one is not a chiral center. As you can see, it has a double bond. This one is not a chiral center. Here we have 3 hydrogens, so it's not a chiral center. This one is not a chiral center as it's attached to the same groups. This is not a chiral center, and this is not a chiral center. So this one is actually a chiral center as it's attached to the OH, it's attached to this group, to this one, and to this one. So it's attached to 4 different groups. So we are going to end up having 3 chiral center. So for this part, it's going to be C15H20O4. And for this one, we're going to have 3 chiral center for this structure formula. Now for the next question, they're asking about the hybridization of carbon atoms in iodine. So the hybridization can be sp3, sp2, or sp. Now if it was sp3, then we would have 4 electron regions around the carbon atom. If it was sp2, then we would have 3 electron regions. If it was sp, then we would have 2 electron regions. And remember that the double covalent bonds or the triple covalent bonds, they count as 1. Now for this structure, we have carbon that has 4 electron regions around it. We have it's attached to it has 4 single covalent bonds. So we have carbons which are sp3, and we also have carbons which are sp2, because we have, as you can see over here, we have the hydrogen, we have the double covalent bond, and we have this bond over here. So we have 3 electron regions. So in this structure, we only have sp3 and sp2. So these are the only hybridization for carbon atoms in iodine. So it's sp3 and sp2. Now the bond angles. Now for sp3, the bond angle is 109.5 degree. For sp2, it's going to be 120 degree. sp3 carbons, they have the tetrahedral shape, and sp2, they have the trigonal planar shape. Question 2. The structural formula of compound X is represented below. How many stereoisomers does this compound have? Now, typically we use 2 to the power of n, where n represents the number of double bonds that we have in this drawing. So actually we have 3 double bonds. So if you use the formula, then 2 to the power of 3 is equal to 8. However, since this compound X is actually symmetrical, so we can divide by 2, so it's symmetrical. So therefore, the number of stereoisomers is going to be divided by 2. We're going to need to divide this by 2. Therefore, the number of stereoisomers is going to be actually 4, because we're going to do 8 divided by 2, and it's going to be 4. And this is due to symmetry, which makes the image pairs identical. So because we have symmetry. Now, what is the percentage of carbon by mass in this compound? So but the percentage of carbon by mass in this compound, let's first determine how many carbons do we have. So 1, 2, 3, 4, 5, 6, 7, and 8. So we have 8 carbons. And the number of hydrogens are, here we're going to have 3. Here we're going to have 1. And here we're going to have 3. So if we count the number of hydrogen, here we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 hydrogens. So to find the mass, or to find the percentage by mass of carbon in this compound, we're going to use the formula, which is the mass of the element, that's going to be carbon, multiplied by the subscript, and divided by the total molar mass of the compound. And we're going to multiply it by 100 because they need this as a percentage. So we need to use this formula. Now the mass of element, which is carbon, is 12, and we have 8 carbons, so it's 12 times 8. And we're going to divide the total molar mass, which is 8 times 12 for the carbon, plus 12 times 1 for the hydrogens, and we're going to multiply this by 100, and we're going to get an answer of 88.88%. And this is going to be the percentage of carbon by mass in this compound, because the molar mass of carbon is equal to 12 and the molar mass of hydrogen is equal to 1. Now for question 3, consider the structure of the organic molecule below. They said choose the correct answer to complete the following on describing the carbon atom that's labeled A. So for the carbon atom that is labeled A, the type of hybrid orbitals in the carbon atom. So as you can see, this A has only 2 electron regions, as double bonds and triple bonds count as only 1 electron region. So we have 2 electron regions, so it's going to be sp. And the bond angle for an sp carbon is 180 degree. And the type of bonds that are formed by the carbon atom, so they mean over here if they are sigma or if they are pi bonds. And actually we have sigma and we have pi bonds. Now remember, if it's a single bond, if it's only going to be a sigma. However, if it's a double bond, then we're going to have a double bond is actually has 1 sigma and 1 pi, and a triple bond, as in this one, has 1 sigma and 2 pi bonds. Now for the other one, they said look at the carbon that's labeled B. Now for B, we need to do the same thing. This B is attached, or it has 4 electron regions around it, so this carbon is going to be sp3. So it's going to be sp3. It has an angle of 109.5 degrees, and it's tetrahedral, and the type of bonds formed by the carbon atom are only sigma bonds, as we only have single covalent bonds around it. Now for carbon C over here, It has 3 electron regions, so it's going to be sp2, and the value for the bond angle is going to be 120 degree, and the type of bonds are sigma and pi bonds. As we have a double bond, so we're going to have a pi bond also, other than the sigma bonds. Question 4, the drug cortisone has the following structure. Cortisol exhibits optical isomers and has a number of chiral centers. Choose the name of 2 different optical isomers. So the correct name is going to be enantiomers. And optical isomers are molecules that have the same molecular formula, and they have the same, so they have the same molecular formula, and they have the same connectivity of atoms. However, they are non-superimposable images of each other. So let's find the number of chiral centers in the cortisol molecule. So for this one, so first let me cancel the ones which are definitely not a chiral center. Now this one over here has 2 hydrogens, so it's not going to be a chiral center. This one has the double bond, so it's not going to be a chiral center. I'm crossing the ones that have 2 hydrogens attached to them. These are not chiral center, and the one that have a double bond. So as you can see, these are definitely not chiral centers. Now this is a chiral center as it's attached to 4 different groups. It has the OH, it has this one. So we have 4 different groups that are present. This one is a chiral center. Now this one is definitely not a chiral center, so I'm going to put an X as it has 3 hydrogens. And this one is not a chiral center as it has 2 hydrogens. This one is also not, and this one is also not a chiral center. Now this one over here is a chiral center as it's attached to the four different groups. Let's continue. So this one is a chiral center as it's also attached to 4 different groups, also in hydrogen. And we also have this one as a chiral center as it's attached also to 4 different groups. It also has hydrogen. This one is not a chiral center, this one is not a chiral center, and this one is not a chiral center as they have many hydrogens. Now for this one, this is a chiral center as it has this group, this one, and it has also a hydrogen, so it is also a chiral center. So let me now count the number of chiral centers that I got. So I have 1, 2, 3, 4, 5, 6. So I have 6 chiral centers in the cortisol structure. So we have 6 chiral centers. Now, in question 4, they also said that another organic molecule is 1,3-cyclobutane dicarboxylic acid, and this is the structure for this organic molecule. And they said identify the type of stereoisomerism that is exhibited in this molecule. And this is a cyclic ring, and we have these substituents on this ring. We do not have a chiral center, so these are not going to be optical isomers as we do not have any chiral center. However, we could have these groups attached on the same side or on the opposite side. So it could be dashed, and here it could be dashed, or this one could be dashed, and we could have like a wedge over here. So they could be attached on opposite sides. And since we don't have a chiral center, therefore the stereoisomerism that's exhibited in this molecule is only geometrical. So it's geometrical isomerism. Table below shows the reactants and products of a reaction. Complete the table. So first we are given the reaction. We need to know if this reaction is an addition, substitution, or an elimination. And we need to know if the reagent that's used is a nucleophile, electrophile, or a free radical. So for the first one, we have bromoethane, and bromoethane is CH3, CH2Br, and we're going to end up with C3CH2 NH2, which is ethylamine. Now this one is a substitution as we are substituting Br over here with NH2. And to do this reaction, we actually use NH3, ammonia. And ammonia is going to be our nucleophile. So it's going to make Br, Br is going to be the leaving group, and we're going to have the NH2 around. So this is a nucleophile that's being used. Now for the other one, we have ethane, and we're going to bromoethane. This should be bromoethane. So we're going from an alkane to a halogenoalkane where we have a bromine instead of a hydrogen. So we're going to have CH3CH2Br, and ethane is CH3CH3. So one hydrogen is going to be substituted for a bromine. So this is substitution. I need to be familiar that the alkanes undergo a free radical substitution. Now for the other one, we have a ketone, CH3, we're going to write it above, double bond OCH3, and we're going to form CH3COH, then this is going to be a CN, and then CH3. So we're actually going to form, we're actually going to add a nucleophile, which is the cyanide. CN- is going to attack the electrophilic carbon over here, as this carbon has a partial positive charge and the oxygen has a partial negative charge. So we're adding a nucleophiles and the hydroxyl group. So this is addition, type of reagent, nucleophile, which is mainly the CN, the cyanide. Now in the last one, we have butan-2-ol. This is an alcohol, and we're going to form an alkene. Now this is actually a dehydration. It's an elimination reaction, because we are eliminating the water molecule from alcohol. So we're removing this water molecule, so it's an elimination. Now the type of reagent that's used in this reaction is usually an acid catalyst. It is either H2SO4, or we could use, for example, H3PO4. Now question 6. In the mechanism to produce butan-2-ol from butene, the following species is produced. This one over here, as you can see, we have a plus on this carbon. So identify the type of species. This is a carbocation. And is it an electrophile or nucleophile? Because we have this positive charge on the carbon, it's definitely an electrophile. Including butene, how many isomers, structural and stereoisomers, does this compound have? So let's start with butene. Now for butene, we're going to have cis and trans. And this is because this carbon is attached to a hydrogen and another group, which is CH3, and this carbon is attached to a hydrogen and another group, which is CH3. Now if they're on the same side, they could be cis. If they're on opposite side, they could be trans. So now we have two stereoisomers for butene. Now for another structure for butene could be a structural isomer. And structure, we mean that they are compounds with the same molecular formula, but they have a different structure formula. So this one has a different structure formula than butene. It's actually but-1-ene. So this is another structure formula. Now we have 2 plus 1, so now we have 3. Another one is the cyclobutane, which is a structural isomer for butene. It has the same molecular formula. We also have cyclopropane with a substituent, a methyl substituent attached to it. This is also an isomer for butene. And the final one is 2-methyl propene, and this is another isomer. Now we don't have a hydrogen over here, so we have double bond, and this is another structural isomer for the butene. So we're going to end up with 2 plus 1, 3, 4, 5, and 6 isomers for butene, including the structure and the stereoisomers. Determine the molecular formula of the following compound. So let's first count how many carbons do we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now we have 12 carbons. Let's count the number of hydrogens that we have. So here we're going to have 3 hydrogens. Here we're also going to have 3, so we're going to have 6. Then this one's going to have 1, 7, 8, 9, 10, 11, 12, 13. And then here we're going to have 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And we're also going to have 1 hydrogen coming out because this is attached to 3. So we're also going to have the hydrogen over here. So we're going to end up with 24 hydrogens. So it's going to be C12H24. How many sigma and pi bonds are present in the following compound? So we have a double covalent bond and we have a triple covalent bond. This double covalent bond has one pi bond and this one has two pi bonds. So we're going to have 3 pi bonds for this compound. Now let's count the number of sigma bonds. Now one thing that students forget is that they need to account for the bonds between the carbon and hydrogen, because these are also sigma bonds that are not visible, but we need to make sure that we count them. So over here we're going to have, let's first count the ones that are visible. So here we're going to have 1 sigma bond. This is 2, 3, 4, 5, and 6. So now we have 6 sigma bonds that are visible. Let's now count the ones which are not between the carbons and between the carbon and the hydrogen. So for this one, we're going to have 2. For this one, we're going to have 1. For this one, we're going to have 2. For this one, we're going to have a 1, 3 for this one. And this one is not connected to any hydrogens, so we already accounted for the sigma bonds. And this one, we have 1 sigma bond. So if you add these, we're going to get 2 plus 1, 3 plus 3, 6, 8, 9, and 10. So we also have an extra of 10 sigma bonds. Therefore, we're going to get 3 pi bonds and 16 sigma bonds for this compound. Give the systematic name for this compound over here. So let's now first, let's draw this again. Now, something that's in parentheses is actually a branch for this carbon that is to the left. So if I'm going to draw it again, it's going to be CH3, CH2, CH. There's a CH3 over here. There's a CH, double bond, CH, CH3. So let's count the longest chain, and we need to give priority to the double bond. So we're going to count from this side, 1, 2, 3, 4, 5, and 6. Now on the 4th carbon, we have methyl. So it's 4-methyl. And we have a double bond on the 2nd carbon. So it's going to be, and we have 6, so it's hex. And we're going to put a dash, 2, dash, ene. Compound X is an aldehyde that has a molecular formula of CXHYO, and the percentage by mass of carbon is 66.7%. Give its molecular formula. Now the general molecular formula for an aldehyde is CnH2nO. And since they gave us the percentage by mass of an element, we can use this formula, which is the mass of the element multiplied by the subscript over the molar mass of the compound times 100. And it's going to give us 66.7 for carbon. Now the mass of carbon, the molar mass of carbon, is equal to 12. So if I put 12 and I multiply it by the subscript, which is N, for the aldehyde, and I divide it by the total molar mass, which is 12N plus 2N for hydrogen plus 16 for oxygen, as 16 doesn't the subscript for oxygen is 1, and I multiply it by 100, and the answer is equal to 66.7. Now if I divide by 100, then it's going to be 0.667, and the N that I'm going to end up with is going to be equal to 4. Now substituting this the N over here, so we're going to end up with C4H8O. This is the formula, the molecular formula for this aldehyde. In the next question, they said select the possible structure formula of compound X. Now compound X is made up of 4 carbons. It's an aldehyde. So let's start with the first one. Here we have 3, 4, 5 carbons, so this is incorrect. Now this is made up of 4 carbons, so this is correct. And this is made up of also 4 carbons, so this is correct. This is made up of 1, 2, 3, 4, 5, 6 carbons, so this is incorrect. So the only correct possible structure formula of compound X is this one and this one. Question 11. Consider the following compounds. We have 4 different compounds. Give the systematic name for compound B. So let's count the longest chain. So we have 1, 2, 3, 4, 5 carbons. This is the main chain. it's a ketone, as we have a carbonyl group over here, and we have a substituent. If there's a branching, we have a methyl on the carbon number 4, and I started numbering from this side because I'm giving priority to the functional group, which is the C double bond O. So we're going to have a 4 methyl, because we have a methyl on the 4th carbon, and because it's made up of 5 carbons, so it's pent and pentan, and we're going to have the carbonyl group on the 2nd carbon, so it's pentan 2 on, to indicate that the carbonyl group C double bond O is on the 2nd carbon. Choose the 2 compounds that belong to the same homologous series. So we need to identify which ones do belong to the same, if they're both aldehyde, both ketones. So this is an alkene. This is actually a carboxylic acid. D is a carboxylic acid, A is an alkene, B is actually a ketone, and C is a ketone, as it has also the C double bond O. Therefore, the 2 compounds that belong to the same homologous series are B and C, since they are both ketones. Question 12, give the systematic name for the following compound. So first, let's count the longest chain, and we need to count from this carbon, as it's the functional group, it's a nitrile group. So we have 1, 2, 3, 4, 5, 6, and 7. Now, some students might count as 1, 2, 3, 4, 5, and 6. This is not the longest chain. This doesn't work because the longest chain is made up of 7 carbons and not 6. So we need to pick the longest chain. Therefore, this is correct. Now, we need to check where are the substituents. So we have on carbon number 4, we have this, which is an ethyl group. So it's going to be 4-ethyl, and we have 7 carbons, so heptane, and this group is the nitrile group. So 4-ethyl heptane nitrile. This is the systematic name for the following compound. Question 13. An organic compound CXHYClZ has the percentage composition of 24.74% carbon, 2.06% hydrogen, and 73.2% chlorine, and its relative molecular mass is 97. Find the empirical formula for CXHYClZ. Write your answer in the same order as in the question. So to find the empirical formula, first I'm going to assume 100 grams, and I'm going to put the carbon and the hydrogen and the Cl in a table. And here we're going to have the Cl. So after assuming 100 grams, I'm going to find the mass in 100 grams, and it's going to be the same as the percentage. So for carbon, we're going to have 24.74 grams. For the hydrogen, we're going to have 2.06 grams. And for the chlorine, we're going to have 73.2. And then I'm going to find the number of moles. Now for carbon, it's 12. For H, it's equal to 1. For oxygen, it's equal to 16. So I'm going to divide each by its molar mass. So for this one, we're going to get 24.74 divided by 12. This one, we're going to divide this by 1, so it's going to be the same. And this one, if we divide it by, we have chlorine, not oxygen. So Cl is equal to 35.5. So if we divide 73.2 by 35.5, so we're going to have an answer of 2.06. And then if we divide by the smallest number, and they all have the same number, so we're going to end up with 1, 1. Therefore, the empirical formula is CHCl. This is the empirical formula for this compound. So the empirical formula is CHCl. Now, in the next question, they said, give the molecular formula and write your answer in the same order as in the question. So to find the molecular formula, I will use this formula. Molecular formula is actually equal to the empirical formula that we got, and I will multiply the empirical formula by the subscript x. Now x is equal to the molar mass over the mass of the empirical formula. Now the molar mass is given as 97. Now the mass of the empirical formula, which is this one, is equal to 12 for carbon, 1 for hydrogen, and 35.5 for chlorine, and we're going to end up with 48.5. So if I divide 97 by 48.5, I'm going to end up with 2. So therefore, if the empirical formula is CHCl and I multiply it by 2, we're going to get C2H2Cl2. What type of isomers can this compound have? So this is the molecular formula. This is actually an alkene. Alkane, like ethane, has 6 hydrogen atoms. If we substitute it by 2 chlorine, it will become C2H4Cl2. However, as you can see in this case, we have 2 less hydrogens, so this definitely is an alkene. We have a double bond between the carbon atoms. So the type of isomers that this compound have, first let's draw the structure. So we have C double bond C. We could have an H on this side and the chlorine on the same side, or we might have a CHCl and double bond CHCl. So the chlorines could be on the same carbon or they could be on different carbons. Now for this one, these are isomers, we call them the positional isomers. So we could have positional isomerism because the chlorine can be attached on the same carbon, or it could be attached, the 2 chlorine atoms could be attached on different carbon. And for this one, we might have a cis and trans isomerism. So we might also have cis and trans. This is another type. This is because we might have the Cl on the same side and we have cis, or we might have a Cl over here and the other Cl on the opposite side, and it would be trans. Next question, they said give the names of the isomers this compound have. So this compound can have the cis 1,2-dichloroethene. It's an alkene. And this is because we have C double bond C. We would have a Cl, hydrogen, and hydrogen. This would be the cis isomer. And we might have the trans, which is trans 1,2-dichloroethene. In this case, we might have the Cl above and then the Cl, another Cl on the opposite side. This is the trans. And we might also add the 1,1-dichloroethene, which is another isomer also for this compound. Question 14, given the following isomers for C3H6Cl2, so we have A and B, give the name for the 2 isomer A and isomer B. Now for A, we have a chlorine on the first carbon and on the second carbon, and the long chain is made up of 3 carbons, so it's going to be 1,2-dichloropropane. This is the first one. And for the second one, we have the Cl atoms on the first carbon and on the third carbon, and the longest chain is also made up of 3, so it's going to be 1,3-dichloropropane. So this is going to be the answer for isomer A and for isomer B. Now for question 4, choose the type of isomerism shown. As you can see, they're exactly the same, but the Cl is on another carbon. So these we call them positional isomerism. Positional isomerism. Now for the next one, they said give the name for the 2 isomer. Now this one is an aldehyde, and this is a ketone. The name for the first one, which is an aldehyde, is made up of 3 carbons, so it's going to be propanal for C. And for D, it's going to be propan 2O and E. So these two are actually functional group isomerism. They are functional group. And this is because this is a ketone and this is an aldehyde. So we're talking about 2 different homologous series, and we're talking about functional group. However, the first one was positional because we still have the same type of group attached to A and B. Now choose the type of isomerism exhibited by chlorofluoroiodomethane. So chlorofluoroiodomethane is CH, Cl, F, and I. So this C is going to be attached to fluorine, to iodine, to Cl, and to hydrogen. And therefore it's going to be attached to 4 different atoms, and it's going to be a chiral center. And chiral centers, they exhibit the optical isomerism. So they are optical isomers. Question 15. Consider the aldehyde C5H10O. This aldehyde has 4 structural isomers. Isomer A has straight chain of carbon atoms. Isomer B has a chiral center. Isomer C has 1 methyl branch. And isomer D has 2 methyl branches. Give the name of the homologous series that is the functional group or the functional isomer of the aldehyde. So another group that has the C double bond O, the carbonyl group, is the ketone. Give the systematic name of each isomer. So we have to draw these isomers and we have to give their names. Now for A, it's going to be a straight chain. So this is isomer A. We're going to have a straight chain. This is actually pentanal. For isomer B, they need a chiral center. So in order to form this chiral center, we have to keep the number of carbon atoms equal to 5, and I have to add a methyl group over here. Now this is a chiral center because we have this group, the ethyl, the methyl, and this group over here. And we also have the hydrogen. So we have 4 different groups around this carbon, and this is called 2-methyl-butanal. Now for isomer C, we need 1 methyl branch, and we don't need any chiral center. So this is going to be isomer C. Now isomer C doesn't have any chiral center. This is because this carbon over here is attached to 2 methyl groups, so they are the same group. And this is going to be 3-methyl-butanal. Now for isomer D, they need 2 methyl branches. So isomer D is going to be this one. There's no chiral center as this carbon is attached to 3 similar groups. And it's going to be 2,2-dimethyl-propanol. Isomer A of the aldehyde C5H10O reacts with acidified potassium permanganate to give compound X. The structure formula for isomer A, we drew it before. It was C3, CH2, 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 C double bond OH, and it's called pentanal. Now it's going to react with the acidified potassium permanganate. So the pentanal is going to react with the acidified potassium permanganate, and the acidified potassium permanganate is actually an oxidizing agent. It's going to oxidize the pentanal and it's going to make it a carboxylic acid, as aldehydes are oxidized into carboxylic acids. Give the molecular formula of compound X, which is the carboxylic acid. Now carboxylic acid have the general formula CnH2nO2. So for n equal to 5, it's going to be C5H10O2. We're going to add an oxygen as aldehyde is oxidized now. Give the name of the product. So the pentanal, which is the aldehyde, is going to be oxidized into the carboxylic acid, which is pentanoic acid. So the name of the product is pentanoic acid. What's the type of this reaction? This reaction is an oxidation reaction, as we're using an oxidizing agent, which is KMnO4, potassium permanganate. For question 16, the molecule C7H16 is an undesirable component of fuel because it reacts explosively in an engine. Give the name of the homologous series that the compound belongs to. So this compound has the formula, which is CnH2n plus 2. So it's going to be an alkane. What's the type of hybridized orbital that C atoms have in the compound? So the hybridized orbitals are sp3, as alkanes only form single covalent bonds. We do not have a double covalent or triple covalent bond. Now C7H16 has 9 structural isomers, only 2 of which have chiral carbon. Give the systematic name of the isomer that has chiral carbon and 1 methyl branch. So we have 7 carbons, and we need to draw the isomer that has a chiral carbon. So the isomer, so we need to draw first 6 carbons, and we need to know where to place the methyl. So if I place the methyl, for example, on this part, on this carbon, then I'm going to form a chiral center because this carbon over here is attached to this group, which is an ethyl, and the methyl and the propyl group, and it's also attached to the hydrogen. So I have 4 different groups attached to this carbon. So this carbon is going to be a chiral center, and the name of this isomer is going to be 3-methylhexane because we have 1, 2, 3, 4, 5, 6. So On the third carbon, we have a methyl group, and the longest chain is made up of 6 carbons, so it's going to be hexane. And this is the methyl. Now remember that branching takes place when the carbon is connected to at least 3 other carbon atoms. So the branching over here is at this carbon, as this carbon is attached to 3 different carbons. So it must be connected to 3 carbon atoms for branching to take place. Now they said in the next question, the question was give the systematic name of the isomer with 3 branches. So if I need 3 branches and I have C7H16, then first I need to draw 4 carbons and then add the 3 other carbons as branched. So here I drew 4 carbons and I added the 3 carbons for them to be branched, and the branching took place at the second carbon and at the third carbon. So here I have 3 branches, 1, 2, and 3. And if I want to name it, I will start numbering from here, 1, 2, 3, 4. So I shouldn't start numbering from this side, as I need to give the groups the lowest possible number. I need to give these 2 groups the lowest possible number, which is 2. So 1, 2, 3, and 4. On the second carbon, we have 2-methyl. Here we have 3-methyl. So we have to use trimethyl and specify their position. And the longest chain is made up of 4 carbons, so it is butane. Monochloroheptane can be obtained by the following reaction. This is the reaction that's taking place. As you can see, we have an alkane. It's reacting with chlorine. And they said, what's the name of the mechanism taking place in the above reaction in the presence of UV light? Now we need to remember something, that alkanes do not undergo mainly addition reactions. Typically they do the substitution, a free radical substitution reaction. And here we're going to have Cl radical after the homolytic fission takes place. And this and the Cl is going to be substituted with a hydrogen. So the name of the mechanism is free radical substitution. And typically alkanes only undergo the free radical substitution, and they undergo combustion reactions, as alkanes are unreactive. So the next question was, what is produced in the first step? Now in a free radical substitution reaction, the first step is initiation, where we are going to form a radical from the homolytic fission. So first we're going to have the Cl and the Cl, and we're going to have the electrons, the bond splitting equally, and the electrons going back to each Cl. So we're going to have a Cl radical and another Cl radical. So the first thing that's produced in the first step is this Cl radical. Now, what's the name given for the last step in the mechanism? For a free radical substitution, the first step is the initiation. Then we have the propagation. And then we have the termination. So the last step in the mechanism is termination. Now for question 17, the structure formula of compound X is represented below. Give the systematic name of compound X. So first I need to number the substituents. So I'm going to start with bromine. So bromine is prioritized first. And then on the second carbon, we have a methyl. Now I shouldn't number this way as 1, 2, 3, 4, 5, 6, because I have to give the substituents the least possible number. So it's going to be 1 and 2. So the name of this compound will be 1-bromo, as B starts before M, methyl, so alphabetically. And then we're going to have 2-methyl. And this is a ring that's made up of 6 carbons, so it's cyclohexane. So the correct name is 1-bromo 2-methyl cyclohexane. Now for the next question, they said, how many chiral centers does compound X have? So let's erase this one. So chiral center is a carbon that is attached to 4 different groups. So this carbon over here is attached to the bromine, it's attached to this group and to this group, and there's also a hydrogen. So here we have a chiral center. Now, this is not a chiral center as it has two hydrogen atoms. This is not, and this is not a chiral, and this is not a chiral center. Let's check if this one is a chiral center. It's attached to a methyl group, to this group, to this group, and it also has a hydrogen. So this is another chiral center. So the number of chiral centers is going to be 2. Now for the how many stereoisomers does this compound have? So because we have 2 chiral centers, I'm going to use the formula 2 to the power of n, where n is the number of chiral centers that we have. So 2 to the power of 2, and we're going to have 4 stereoisomers. Now remember that cis trans aspect is already incorporated in this formula. So if these are wedged, both of them are wedged, or one is dashed and the other one is wedged. So this is already incorporated into this calculation because the cis trans aspect, we take it into part of this as a part of this formula based on the chirality. Ethanol C2H5 can be prepared by various chemical processes. The chemical equations below represent some of these processes. Identify the type of each organic reaction, whether it's addition, reduction, oxidation, elimination, or hydrolysis. For the first one, we have C2H5I plus water. It's giving ethanol plus hydrogen iodide. So over here, water is used to break a bond, and it's going to replace the iodine. And whenever we have water that is being used to break a bond, we refer to this as hydrolysis. Now for the second one, we have C2H4, and C2H4 is an alkene. And we're having water. It's reacting with water, and it's forming the ethanol. So we're going from an alkene to an alcohol. So water is going to add across the double bond. And when water adds across the double bond, this is an addition reaction. And I just want to note that when we're going from the ethanol, so as in the opposite way, from ethanol to the alkene, this is an elimination reaction. And we're going from an alkene to form the ethanol, we're adding water. So this is an addition reaction. For the third one, we have C2H4O plus 2H giving ethanol. So we are adding hydrogen. Whenever you see hydrogen in bracket, this is definitely a reduction reaction. If you saw, for example, oxygen in bracket, then it's going to be oxidation. However, we have over here hydrogen. Now, for question 18, we were also given the below diagram. The below diagram shows one step in the mechanism of the hydration of ethene. Identify the type of each species above, whether it's a nucleophile or an electrophile. So this one over here is the electrophile, as it has a positive charge, so it's electron poor, it's electron deficient. And this one over here is going to be the nucleophile. It is electron rich, it has a lone pair, and the lone pair is attacking the partially positive carbon. Now, a student produced ethanol by reacting 560 grams of ethene with steam in the presence of concentrated phosphoric acid at a temperature of 330 degrees Celsius and 6 megapascal. The mass ethanol extracted from this process is 760 grams. We are given the molar mass for each atom. Calculate the mass of ethanol if the yield had been 100% and give your answer to 3 significant figures. So first, I need to write the reaction again over here. And I have to determine the number of moles of the reactant that I have used, which is C2H4. Now, H2O is typically in excess in this reaction whenever we react an alkene with steam. So this is used in excess, the steam. And so therefore, I have to find the number of moles for the limiting reactant, which is ethene. I do mass over molar mass. 560 grams divided by the molar mass, which is 2 times 12 plus 4. I get 20 moles. And then using the reaction ratio, I'm going to get the number of moles for the ethanol. It's going to be 20, the same as the ethene. And I would use this formula, which is mass equal to the number of moles times the molar mass. And the final answer is going to be 920 grams. So these are 3 significant figures. I could add a dot over here so that the zeros should be counted. So if the percentage yield is 100%, the mass produced is 920 grams. Now in the next question, they said calculate the percentage yield of ethanol and give your answer to 3 significant figures. So to find the percentage yield, I have to use this formula, which is the actual mass of ethanol over the theoretical mass multiplied by 100. The actual mass that I have is 760, and the mass that I got is 920 grams. So I divide them and I multiply them by 100. The answer is going to be 82.6%, 3 significant figures. Question 19, identify the type of fission occurring in each of the following steps, whether it's homolytic or heterolytic fission. So a homolytic fission is when a bond splits equally, producing 2 free radicals. And a heterolytic fission, bond splits unequally, producing a cation and an anion. So the heterolytic fission is this one, and the homolytic fission is this one, where we're forming the radical. Question 20, consider the following mechanism. So we have compound A, we have the CN. They said give the molecular formula of compound A. So let's count how many carbons do we have. We have 1, 2, 3, 4 carbons, C4. Let's count the hydrogens. So here we're going to have 3 hydrogens. Here we're going to have also 3 hydrogens. And here we're going to have also 1 hydrogen, and we need to account for this hydrogen over here. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 hydrogens. And we also have an oxygen atom. Give the systematic name of compound A. So let's find out the longest carbon chain. So it's going to be this carbon 1, 2, and 3. And on carbon 2, we have the methyl group. So it's going to be 2-methyl propanal, as this is an aldehyde, since it has this C double bond OH. So an aldehyde has a C double bond OH, so we need to end the name with al, Al. Now, what's the type of reaction in step 1? So we're using the CN, the cyanide, and it's being added to this partially positive carbon. As you can see, we have an oxygen, so this carbon is going to be positive, and this is going to be negative. This is an electrophilic site. The CN is going to be added over here, so this type of reaction is a nucleophilic addition, as we're adding the CN, and then we're adding the OH, the hydroxyl group. So this is a nucleophilic addition. Remember, CN is the nucleophile. Which hybridized orbital is not present in a compound B? So one thing that I have to note is that CN is actually C triple bond N, and it's present over here. So this C triple bond N, this carbon over here has the orbital which is sp. So it has the hybridized orbital sp. And we also have carbons which have the sp3. However, we do not have a double bond and a single covalent bond carbon to form the sp2. So the only hybridized orbital that's not present is actually the sp2 hybridized orbital. Now for question 21, we need to identify to which organic family does each functional group belongs to. For the first one, we have the C carbonyl group between 2 carbon atoms, so it's a ketone, not an aldehyde, as aldehyde have the C double bond OH at the end. It's not between 2 carbon atoms, as in this one, so this one is an aldehyde. This is an amine, and this one over here where we have C double bond OO, this is an ester.